Okay, so in the last video we did a formal derivation of some perturbation theory, and in this video we will do some practice questions and look at some consequences. So firstly I want to summarize what we did last time. So I'll talk as I write a little bit, and you may just want to speed it up. So we've got the problem that we need to solve is H equals H naught plus V. Now I'm just going to, this is how you usually see it. So I'm going to absorb the lambda into V. So note, lambda is absorbed into V. But remember that there's an order by order expansion in the smallness of V now. And in that order by order expansion, we can write psi n, the exact solution, as the unperturbed solution plus first order correction and so on. We didn't get a higher order. And similarly, that the energy was the unperturbed energy plus a shifted energy plus second order and so on. And we derived expressions for those. And this is the summary of it. Delta En1, the first order correction, was psi n naught V psi n naught, which we gave us the name Vnn, the matrix element of V in the unperturbed basis. We got the second order correction to the energy, which we wrote as Vmn squared over En naught minus Em naught. And we have the first order correction to the wave function, which is the sum over states Vmn over En naught minus Em naught times psi m naught. Okay. And what we didn't get to last time is talking about the conditions of applicability. So it's probably a good time to do that now. So conditions of applicability. When can you use it? So firstly, we need that V or lambda V is small. And what does small mean in this case? It means that the energy denominators that we see in delta En2 and delta psi n1 are small. So we need the shift in the energy to be much, much less than the spacing between energy levels. If that was not the case, then you wouldn't be able to keep the same ordering of the levels necessarily, and so that's not a small perturbation anymore. And the second thing is that if you look at this term here, you want the correction to the wave function to be small. So this term of the wave function should be small. And that simply just means that we want the magnitude of Vnm to be much, much less than En naught minus Em naught. Okay, so that's the conditions of applicability. So if both of those things are true, then we're in a good place to use perturbation theory. So now let's do an example. And so the example I want to do, I should change my pen color, maybe dark blue. There we go. Example. And this is either from or similar to a question in Griffiths. So often we will start these kinds of problems with exactly solvable H naught, and in this case the square well is exactly solvable, or at least the infinite square well is. So you've got a square well, infinite square well, confined between minus a on 2 and plus a on 2, and you have the perturbation with perturbation v equals alpha times delta x, where alpha is just a number. And the delta here is the Dirac delta function. So in other words, it's a perturbation that applies only at x equals 0. Everywhere else, it's 0. But it has finite, when you integrate over it, it's finite. So this is a typical kind of problem. It's a square well because we have the solutions. Other examples where we have exact solutions are like the Coulomb problem or the harmonic oscillator, and that's pretty much it. Like, we're always going to ask questions about Coulomb problem, harmonic oscillator, and square well because they're the ones that are the easiest to answer and the ones we're most familiar with. So when we are expanding our basis, we know what we're working with. And so that's the perturbation. And then the questions would be something like find 1 delta E n 1 for all states, and 2 delta psi 1 for the ground state. So let's see how we go. So let me draw the problem first. So we have a square well with infinite sides. It's supposed to be a square. That's 0, a over 2 minus a over 2, and it'll have solutions that look something like this. First one, second one, third one, etc. And that'll be n equals 1, n equals 2, n equals 3. And the perturbation now looks like a little blip at 0. So that's alpha times delta x is looks something like this. Of course, it doesn't have any width because it's a delta function, but this is a good way to visualize it. That's the perturbation. And the solutions, we know, psi n 0 is equal to square root 2 over a cos n pi x over a. That's for n equal to 1, 3, 5, etc. We've got, that's the even solutions. We've got the odd solutions, odd parity I mean, which is sine functions. These are for n equals 2, 4, etc. And then we've got en0 equals h bar squared pi squared over 2m a squared times n squared. So that should be very familiar to you, and you should be able to derive that very easily, or just remember that there are cos ones and sine ones. Get the boundary conditions to work out it's cos of what, sine of what, and then normalize it. Square root 2 over a. I always forget the normalization, but the rest of it's not too bad. Okay, so let's do our two parts. Firstly, we want to find the first thing we want to do is find delta En1, and the second thing we want to find delta psi1 for the ground state. So the first thing we want is the energy shift. And the energy shift is nothing but the integral psi n naught v psi n naught. Right? That's what we call v and n, but I write it out here so that we remember what we're doing. So for n odd, we have delta E n1 is equal to the integral minus a over 2 to a over 2 of 2 over a cos squared n pi x over a times alpha times v, right? So times alpha delta x, and integrate that over dx. And if you know how to integrate a delta function, all you do is you take the value at the delta non-zero, and so when you do that, you'll just get the value of cos squared at x equals 0, which is 1, and so you'll end up with 2 over a times alpha, or 2 alpha over a. Okay, that's too easy. The next one, n even, n equals 2, 4, 6, etc. We have delta E n1. Now this time, it's confusing. This one, it's the n is even, but the function is odd. So you get sine squared n pi x over a times alpha delta x dx, and this time sine of 0 equals 0, so this is nothing but equal to 0. Okay, so we've done the first part, which was find delta En for all levels. We know exactly what they are. All the odd levels shift up a little bit, and even levels do nothing at all. Okay, what about the change in the wave function for the ground state? So we're only interested here in delta psi 1, n equals 1, and we're only interested in the first order shift. So we write out our formula, sum m not equal to n, not equal to 1, of Vm1 over E10 minus Em0 times psi m0. Okay, so what's Vm1? You can go and do an integral yourself, and you will find that you get minus 2 alpha over a times, well, you get 2 alpha over a for the integral, and then you'll get only m equals 3, m equals 4 will not be there, m equals 5 will be there, etc. over, and let me just write this as delta E31 plus, and that's where the minus sign comes from the denominator. So 5, 0 over delta E51 plus 7, 9, etc. So it's an infinite sum where delta E M1 is defined as being h bar squared and pi squared over 2m a squared. Ooh, m. This is mass down the denominator here. That's mass. Not well. I'm not going to correct it because it's so common that you need to be able to recognize which one's mass and which one's not mass in everyday life. Mass index. Okay, and so this gives you your correction to the wave function. And so this is pretty much all you can do. You can't really go much further than this. So we'll cut that one off. Okay. So some consequences. So there's a common situation that can occur. Suppose, and this is like a typical thing, suppose that, and it's due to symmetry reasons, and we'll see some examples of that later on. So suppose that the first order correction to the energy vanishes, i.e. Vnn equals 0. We've seen an example of that just now. So for the states up here where we had n even, then we had delta E n1 equal to 0. They were the cases where that's an example of a case where the first order correction to the energy vanishes. Then, in that particular case, we would have a second order correction. Delta En is going to be only starting at second order and will be approximately equal to second order. And that's going to be equal to sum of m not equal to n of Vnm squared over En0 minus Em0. Okay, so what? This has consequences. The first consequence is that the ground state goes down. Since for all terms the denominator is E0 minus Em0 is less than 0 for all m. Right? So for all indexes m where m is not the ground state, the denominator of the equation above, this one here, is less than 0, and the numerator is the absolute value squared, so that's positive. And so each term in this is negative, and so therefore the whole thing is negative. And so in the case where the first order correction to the energy vanishes, the second order correction is the main one, and that means that the ground state goes down. So in other words, you have E0, this is H0, and then after you apply the perturbation, it goes down. Right. The second consequence is that if you have two close levels, then the energy denominator is much bigger for between those two levels than it is between those levels and any other levels that aren't those two levels. So you've got two close levels, repel since denominators are small for those two and have opposite signs for the two levels. All right. So what does that look like? You've got two levels. I don't know, E1, E2, E6 and E7, whatever they are. That's the normal case. That's the unperturbed case rather. And then you apply the perturbation and they repel. This one goes down and this one goes up. And so these are two consequences which are sort of typical consequences which you kind of explain. They help to explain the physics of what's going on. So when you meet people who understand quantum mechanics and they can just kind of guess at what happens when this or that happens, this is the kind of thing that they're relying on. The physical intuition that comes, which says, aha, in this case, the ground state goes down when I have a perturbation. Or you've got these two close levels and I apply any perturbation, I know they're going to separate a little bit. So that's kind of useful and intuitive things that you can use to check your work or to understand the physics of what's going on. The last thing we want to do before I stop is just introduce simple, and I mean simple, Feynman diagrams, because we're ready to do that now. In Feynman diagram language, the first order correction to the energy, delta E1, is just the matrix element VNN. I can represent that in a Feynman diagram as follows. I've got state N and state N and an interaction V. And so this is N coming in, N going out, and the interaction is V. So N coming in, V, N coming out. Typical kind of Feynman diagram. Okay, that's the easiest one. Just a vertex. The next most complicated one would be something like delta E2, which is given by this formula. And this too can be represented by a Feynman diagram. The Feynman diagram looks like this. You've got N coming in, there's an interaction with V, and it becomes M, then you have an interaction with V, it becomes N. And these, another way of writing this would be something like, so this, well, I want to kind of write it in the same way that I did the previous one. I would say something like this is N, well, so the first interaction is N becomes M, whoops, N becomes N due to V, then that N becomes back to N because of V, and then I need to understand what this intermediate state is doing. All right, so I've got the initial state, let me just mark this up. Initial state, psi n 0. I have a final state over here, psi n naught star. I have vertices, which are here, which are V and M. And I have an energy denominator, which should be red. And this is an intermediate state. Intermediate state. And then I have rules like the intermediate state gives me an energy denominator. And furthermore, the intermediate state means that I have to sum over the intermediate state. So I just know that I have to do that. It's in the rules. And I have to have an energy denominator. So there's some rules that people would have. So some rules would be typically you have solid line is a particle or a wave function. You would say a rule such as a dashed line or wavy line is a perturbation. You have a rule that says every vertex gives you a matrix element. And the intermediate state gives you a sum and an energy denominator. Of course, I'm not trying to teach you all of the rules of Feynman diagrams or what they're for and all the context that they're used. It's just a rough overview. So really, I just wanted you to see it so that you don't think it's some kind of deep magic. Feynman diagrams are just a way of expressing terms of perturbation theory, nothing more. So now that we've seen that, I'm going to stop this video and you should do some practice questions on perturbation theory. And when we come back, we'll talk about, in the next video, we'll talk about degenerate perturbation theory. Thanks very much for your attention today.